So this is a little bit going into the third talk. I hope to convince you that I have more to say about it. So I guess my goal is going to be to talk about how selfish mining is really, again, a question that's related more deeply to the security of Bitcoin. I think you saw a glimpse of this in Raphael's talk in the morning when he was actually discussing chain quality as part of the consensus. And selfish mining is something that tries to disrupt chain quality, right? So maybe if I want to place us on the map on where we are in terms of Satoshi's theorem, this is the way I like to look at these problems. It's basically to say that we have these assumptions that give us the security of Bitcoin. One of our assumptions there is that the attacker controls only 50% of the compute power, and somehow the incentives are the things that get us this assumption. Unfortunately, what Itai just basically showed you is that you can gain at the expense of your competitors. You push out others from the blockchain, and in some sense, you make more money. You can grow to become that 50% attacker just by sheerly making more money than everybody else, squeezing them out economically from the game, right? So now, one might ask a question, can we extract a positive result out of what happened? So Itai showed you that the strategy only profits when the attacker has enough compute power. So I call this the alpha, the fraction of hash rate that the attacker has. So maybe one of the figures that Itai showed was 25%. If you take this idea of coin flipping and choosing a chain based on a flipped coin, do you now have resilience up to 25% of the compute power in any single pool's hands? And is the protocol then in equilibrium? Right? If everybody is smaller than 25%, does that imply now that we will follow the rules? And this is a nice positive result that seems to be maybe hiding in there. And the other thing, of course, in addition to the compute power, is this networking capability parameter gamma that Itai also mentioned. So what we really wanted to do is to think about what happens, right, when we do these things, and does this mitigation of Itai and Emin Gunserer is actually good. And there are actually more questions, right? So we were really interested in getting rid of selfish mining, right? This is before work on inclusive protocols and fruit chains really kind of gave us the realizations that we can do this. There were a lot of proposed fixes, right? So Itai and Emin suggested one in their paper, but there were others that were starting to pop up to think about how to redistribute rewards and so on. And really, what we have to do is if you change the mechanism somehow, if you change the way Bitcoin works, you can't keep using the same strategy to try and deviate. Maybe you just fixed it for that specific strategy, but the attacker will now do something else. There's going to be a completely different deviation. So how do we think about these things generally? And more questions are what happens when we start scaling up, right? We know already that when we start to have more transactions per second, more frequent blocks, then the ratio of blocks on the blockchain is not fair. So attacks might also be a problem in that case. Right, so we are interested in somehow in finding the worst case deviations, right? So worst case deviations, not because we're trying to help the attacker, but basically, if we can say the worst case deviation is to play by the rules, then we know that we have an equilibrium, we know that we're safe, and everything is nice. So how do we find the worst case deviations, right? And use those to evaluate potential fixes and so on. So the main result that I want to talk about is basically an algorithm that computes the optimal attack. And this is exactly in the model of, that Itai just showed you. Basically, an attacker with computational power alpha and some networking capability that is represented by this constant gamma. And then we can take this algorithm and somehow tweak it and use it to evaluate modified protocols. And we find them to actually be less resilient than originally thought, right? So we did find better strategies to attack with. And another result that we were working on is what happens when there are delays. Is the protocol still in equilibrium? Can we still give a bound? I mean, if all of the pools are smaller than some amount, than some fraction, is this the case that nobody gains from deviation as well, even when there are delays? So unfortunately, the news is negative, and miners can profit once you account for delays and you change the model a little bit to consider the fact that blocks don't arrive instantly from one place to the other. Okay, so the good news is that the really bad deviations that we do find are not much worse than what Itai has just shown you. The result of Eyal and Sirer is actually very close. So instead of 25% resilience for this coin flipping technique, you get something like 23.2, right? And I'll show you exactly why the threshold is lower. That means that that attackers can still gain even if they're slightly smaller than 25%. Okay, so now, and of course the bad news, like I said before, when you have delays, then miners of any size really can gain from deviating, and maybe we lost our opportunity to get a positive result. That's very unfortunate. And this, in some sense, is very important for the scalability debate, right? If you were talking about increasing block size and increasing the rate of blocks, one of the things that really were bothering people are these things that change the incentives, that change the distribution of payments, that push the system towards centralization, right? If the system it favors larger players by paying them more, by allowing them to deviate more profitably, then we shouldn't be raising the block size, right? That was one of the arguments. So in this case, we don't know exactly the magnitude of the gains. The theorem, I'll show you like a hand-wavy proof later, but it's very small, at least for what we can construct, but we don't really know how much you can gain. And it really does depend on the delay. So let's go over the model really quickly once again, right? We have an attacker that builds blocks with probability alpha. He has alpha fraction of the compute power. We have the honest nodes that have 1 minus alpha fraction, and each block just specifies a single parent, right? We build these things. Occasionally, right, things get off the chain, and we only pay you money if you are on the longest chain, right? That's the main idea. And the parameter gamma that Itai also mentioned basically says that if I, an attacker, have a block ready and I'm withholding it, and the other miners have created a block, and now we rush to spread it in the network, right? I hear that this guy starts to send his block. Right? An attacker can try and match at the same time, and he gets a gamma fraction of the network to accept his block first, and this other guy, right? The honest network only grabs 1 minus gamma of the nodes. Right, so these are the two parameters. It's the exact same model. So now I want you to think about it as a decision problem. From the honest node's perspective, there's a prescribed behavior. Everybody is supposed to mine on the longest chain. You're supposed to break ties in a certain way. You have to publish your block immediately, as the protocol dictates. But the attacker deviates, of course. He can mine anywhere. He can build a block off chain somewhere, or I mean on top of an earlier older block, or he can delay his publication. So maybe there are these blocks that nobody heard of, but there's basically a strategy space here of when do you do that, when do you withhold, when do you publish, and so on. And the desire of the attacker is basically to choose a behavior and to maximize the fraction of his blocks on the chain, right? So the number of blocks he has on the chain versus what everybody else. So now that I phrased it this way, right, you can think of it as a decision problem in some sense. And Itai showed you a specific strategy. We later referred to it as SM1, as selfish mining 1. It's just, I don't know, we picked a name. They didn't, I don't think Itai named his strategy specifically. But basically, their strategy said things like, if the honest chain is longer than yours, then give up, right? Then stop right there. It is a specific behavior. I could have kept working on my secret branch if I wanted. Maybe that's profitable, maybe not. Right? If I am ahead by 1, right, this depends a little bit on the value of gamma, then maybe override the chain. That's maybe another form of behavior. Or if I have a tie, maybe I can release my block at the same time and try to grab that gamma fraction of the blocks. And the analysis, of course, showed that you can only profit if these are large enough. So now, you also saw a theoretical upper bound on what you can make, right? This, Raphael showed you, I think, an example. Basically, if an attacker builds an alpha fraction of the blocks and the network builds a 1 minus alpha fraction, then at best, if you think about it, every time I push, an attacker pushes an honest block out of the chain, he does so by revealing a chain of at least the same length, right? So an attacker's block takes out at most a single honest block. So we can look at the fraction and say, okay, the attacker built alpha blocks. That's what he has. What is the number of blocks that got to the chain? So there are the attacker's blocks, and there should be 1 minus alpha honest blocks here, but an alpha fraction of them, right, was out. So we have 1 minus 2 alpha. So this is basically the fraction of attacker blocks on the chain that you can optimally hope to have. Right? And this is indeed, as Raphael mentioned, a tight result. When the parameter gamma equals 1, basically when the attacker gets ahead and publishes his block to everyone always first, then you can actually reach this exact number. Okay, so now we wanted to start to optimize algorithmically, and we started to think about state, right? So basically there's a situation in the world, right? We have some length of chain for the honest network. We have some length of the chain for the attacker, and we can encode those as LH and LA. There are additional things in the state of the world, whether the network is currently split. Did it currently see 2 chains of equal length, and is it working on them or not? And another is, are we able to, does the attacker have a hidden block prepared in advance that he can publish maybe faster than a competing block if he sees one coming suddenly? So there's basically a way to encode the situation that we currently see. And there are different actions that we might take. One action, for example, is to adopt. We can throw away our secret branch and resume to working on the chain from the start, basically restart the attack. We can try to match, publish a chain of equal length. We can try to override the current chain by 1 if we have a longer chain. That's conditioned on us having more blocks. Or we can wait and basically keep mining on our secret branch if we're the attacker. So you can think of other actions that you might be able to do. Maybe you can open up a 3rd chain here or do other things. But what we do is we show that these actions are sufficient to give you an optimal strategy. Right? You can compose them just from this set of operations. And now we need to decide on what to do. Given the state, which actions do we take? Do we adopt? Do we match? Do we override? Or do we keep working on our secret branch? Right? So there's something specifically tailored to solve these sort of problems. This is, if you've heard of Markov decision processes, a very commonly used tool in artificial intelligence and in learning. Basically, right, an MDP is just a description of a problem very similar to what I just showed you. There's a set of states, right, the situations that you might get to in the world. There's a set of actions that you can take at every state. There's a probability function that tells you that if you take state S, at state S action A, what is the probability that you get to another state, right? So for example, if I work on my secret chain, what is the probability that I build the block, and what is the probability that the honest network will build the block. That will change the state in different ways. And there's a reward function, right? If at state S I take some action and wind up at another state, I get some reward, right? It could be negative, it could be positive. And then MDPs are basically looking for a policy, basically a mapping from states to actions, what to do at any given state, so that I maximize my expected reward over an infinite period of time. So if I keep playing the game, I gather these rewards. If I sum them up and average them, in this case, I take the average reward per round. I want to make as much money as I can, right? How do I maximize this? Okay, so maybe ignore some of the details here about the limits and so on, but trust me that this is the definition. Right, so luckily there's a way to solve MDPs. It's a very nice, very simple algorithm. You can do things like policy iteration, value iteration. There are a lot of good algorithms to solve MDPs. Unfortunately, the problem that I showed you about blockchains, right, and selfish mining is not exactly an MDP. The reward function that we had is not a linear reward function. It's not like every time we build a block, we get 1 unit of reward. We are actually interested in a fraction of blocks that we make, that we manage to get onto the chain. This is something that is not easily represented as just a reward function in the classic MDP sense. Right? So still, the problem is close enough to MDPs that we can have a reduction. We can solve a series of MDPs and actually get an optimal policy. The exact strategy of what you do when you want to deviate. So let me show you, for example, what the MDP looks like. So if, for example, I have a length of the attacker chain LA and an honest network LH, then if I choose to adopt, right, I basically abandon my strategy. I move to either to a state where the attacker has 1 and the network has 0, or to a state where the network has 0 and the attacker has 1. And this is with probability alpha or 1 minus alpha, depending on who builds the block. Right, so this is basically a specification of these state transitions. And for the rewards here, notice that I did not write a single number. I actually wrote 2 numbers. One is the number of blocks that the attacker added to the chain in this event. And one is the number of blocks that the honest network added. Okay, so this is not a classic reward function in the sense of MDPs. But this is what we will use in the reduction. Right, so one more thing that we need to say, the state space, the possibilities for the value of LA and LH are basically infinite. You can have very, very long chains. And from a practical point of view, you cannot solve MDPs that are infinite. So you just truncate them. And we show in the paper how to do lower bounds and upper bounds that kind of say what the error is because of throwing out all of these higher values. And you can do this so that the error is very small. And then what we basically do is we take these states, these actions, these stochastic transitions, and we build a linearized reward scheme. And here's the reward scheme. We pick a parameter rho, and I'll tell you in a second how we pick it. And we're going to give the attacker, every time he puts a block on the chain, we're going to give him 1 minus rho. That's going to be his reward. And every time the honest network puts a block on the chain, he's going to get minus rho. He's going to get a penalty for allowing the network to put a block on the chain. And then we show a theorem basically that says that if you guessed this number rho correctly, somehow I magically knew which rho to pick, right? An optimal policy of an MDP will give you a 0 average reward. Right? We'll give you reward 0. You basically win as often as you lose in some sense. If rho that you picked is the maximal ratio of attacker blocks on the chain. Right? So basically, we can say that if I did this, I built this reward scheme, and I found that the optimal policy gives me 0, then this rho that I picked is the exact optimal ratio of attacker blocks. So how do you really choose rho? You don't pick at random. You can actually do binary search. So we know that the reward of the optimal policy is monotonically decreasing in this value. And so you can actually solve a series of MDPs until you get to the right value. And you get a policy that gives you this value. So let me show you what the policies look like. So for example, so this table should be read in this way, right? So this is the number of honest blocks in the current, since the last split. And this is the number of attacker blocks. And right here in every square, we say what the action is. And the actions are either you wait, you override, or you adopt. And there's a missing action here that should have been matched, but the value of gamma is 0, so the attacker never wins any block races. So this is an action that never appears in this case. But basically what happens now is we do a sort of a random walk in this state space. So for example, we could have started here, and the attacker built a block, then he waited some more, and he built another block, and then the honest network built one. And then the action here is to override the chain. So we basically go back to the start, and the rewards that we collected are 0 for the first action. We didn't add any more blocks to the chain, 0 for the second, and then we added 2 blocks. Each one gives us a reward of 1 minus rho, right? So we can have another go, and with probability alpha, we go this way, and then the action here says basically adopt the honest networks block and abandon your attempt. So we gain a minus rho reward, right? Or another trip might get us this way. We wait a little bit and abandon again, and then we get 3 blocks into the chain by the honest network. Right, so this thing, think of this as going on infinitely. And when you do this game, right, follow these trajectories infinitely, you get some average payment. So if the attacker builds a rho fraction of the blocks, he gets 1 minus rho reward for each one that he puts into the blockchain. And the honest network builds the rest, and you get a penalty of minus rho, then the optimal policy gives you 0. So this is basically kind of a hand-wavy proof of why that theorem was actually correct, or maybe an intuition. Okay, so now here's, right, this is an actual policy that we computed for attackers of size 0.35 and gamma equals 0. And you can notice something very interesting about the attack is that this thing marked in yellow basically says that the attacker will try and keep working on his secret branch even if he falls behind. So if you pick a square here, for example, the honest network has 6 blocks, and the attacker has 4, and still the optimal policy in this case is to keep working on your secret branch even though you are 2 blocks behind. Okay, that turns out to be the optimal policy. And it's very non-intuitive, but we do understand where it came from. It's a little hard maybe to convey, but this is the actual result. So what do we actually get? We take this procedure, and we run it for every value, for example, of alpha, of the attacker. So what you see in this plot is basically if you are a pool of size alpha, what are the rewards that you might gain? So this red line, this red dashed line, is if you're mining honestly, you're going to get an alpha fraction of the rewards when you have an alpha fraction of the compute power. Right? So this is the honest strategy. Itai's strategy is basically this blue line. It goes up, and at some point it departs from the red line, so it's worth it to deviate. And this green line here is the upper bound that I mentioned of alpha over 1 minus alpha, the most that you could ever make. And the optimal policy, what you're seeing here, the circles and the x's are the upper bounds and lower bounds that the computation gives us. So you can see that we make slightly more money than what Itai has shown you, and we actually depart from the honest strategy a little bit earlier. You can't even see it. Okay, so this is how to compute optimal strategy. So it seems like a very low gain, but in some sense, we know now that if this is indeed the case, the optimal strategy in all of this region is to play honestly. So in some sense, we have an equilibrium result. It's a good thing. So this is how the threshold changes, right? So Itai showed you there's a threshold of 1/3 at gamma equals 0. it's actually slightly lower. And so we did an evaluation of a lot of different protocols with this, right? You could still gain with less than 1/3 for classic longest chain. For the Ghost protocol, you do the same. For the random tie breaking, instead of 0.25, you get 0.232. Ethan Hellman had a nice suggestion of freshness preferred. We showed this actually manually, not through the algorithm, that it does even worse than regular Bitcoin when you do a different deviation, and so on. So this looks very nice. Okay, so now maybe the last result is that when you have delay in the network, I told you that these bounds disappear. You can just make money deviating no matter what your size is. And the intuition here is that delay can naturally cause these splits to occur without your deviating from the strategy. So even if I'm playing by the rules, I might be creating maybe 3 blocks in a row before I can even transmit them to the rest of the network. And so by some sheer chance, we might end up in this situation. And it might be that a single miner built maybe 2 of these blocks. So now, according to the protocol, he's supposed to throw this chain away and just work on his version of the longer chain. He wound up here by mistake. But since he has 2 blocks in this branch, he prefers that this branch actually survives because he's going to get a very large reward if he builds another block here. Right? So basically, he will not go to the longer branch. He can choose to extend the shorter one, and that's the deviation. Right? So in some sense, this should be troubling for us. The Bitcoin protocol is not an equilibrium. Right? So we don't know what happens when everybody deviates. It's close to an equilibrium, but it isn't an equilibrium. This is a property of protocols that we'd like to have. So now I really want to talk about the implications for security. Okay, what does selfish mining imply for security of Bitcoin? And I want to get to a very basic notion of security. What are we trying to prove when we try to say Bitcoin is secure somehow? So the security analysis of Bitcoin usually has a statement like this. If you wait for K confirmations on your transactions, then the probability of a double spent block, right, of a double spent transaction will decrease exponentially in this value K that you've selected. Right? So if I choose to wait for 10 confirmations, my probability of double spend is really low. So this is a little bit troubling for me because probabilities, right, can be amplified. You can repeat. So an attacker can carry out silent attacks. For example, he can start to build a branch of the chain on his own, have his double spend transaction in there ready and waiting. And if he sees that he falls behind too far, he hasn't managed to build a lot of blocks, he can retry. Nobody on the network heard anything. He just throws his own block away. And he restarts the attack. Maybe this time he gets a little bit more lucky. He has like a burst of good luck and builds a lot of blocks. Now he knows that he can succeed, for example, if the recipient is only asking for 2 confirmations. Right? So, for example, right, he releases his transactions to the network. He goes to the store, basically pays for something. A block is built. I think it's 1 confirmation maybe. So this guy has a confirmation. He says, OK, I see the transaction in a block. But now the attacker can release his secret chain. He knows that he'll succeed, right, for sure. So all he had to do was silently restart the attack again and again until it works. Right? So in what sense do we have a low probability of being attacked if we can just repeat the attack? Right? So what I argue is that this was not the right notion that we were aiming for. We weren't really trying to talk about the probability. What we were really trying to say is something about the cost. If something is low probability, we'd like to say that the cost of attack, the cost of succeeding is really high. So why would the cost of attack be really high? So supposedly, right, every time I do these things, I try to build these off-chain blocks and fail, they don't get published, and I lose money. Right? And if my chances of success are exponentially small, then I need exponentially many attempts to succeed, and then I pay a lot in lost revenue, right? So this repeated attempt basically cost me a lot of money, right? So this is the main reasoning, but unfortunately, this reasoning is not correct, right? We'd love to say that the cost of attacking in selfish mining is exponentially high, but what I want to show you is that the selfish mining results basically say that that's not the case, right? So what really happens? If you think about the deviation that Itai showed you originally, every once in a while, it overrides the chain with a long chain, right? It overrides the chain. So you can combine a double spend with this, right? If you know that you're going to somehow or sometime override the chain, you can embed that conflicting transaction in here. So the result that I showed you basically was that you don't lose money as a result of doing this with blocks. So it's actually not costing you anything. It's actually a profitable strategy. On top of that, add some more double spending, and you profit even more, right? That only helps you. So in that sense, Bitcoin does not impose a cost on attackers if they combine selfish mining with double spending, right? It's not costly to attack, it's beneficial. So now we're kind of at a loss. In what sense is Bitcoin secure, right? If it's beneficial for attackers to attack. So I want to say that maybe to suggest another alternative, there are different models of security. Maybe the one I'm interested in is to show that as a defender, I may get attacked, but it's not going to happen very often. Or if we talk about cost, I'm not going to suffer very large losses as a result of attack, right? So the attacker might find it beneficial to attack me, but he's going to take very little money over time. So instead, what we might show is, basically the fraction of double spent blocks that we will see on the blockchain is bounded. So this, again, should remind you of chain quality in some sense. This is the number of blocks that the attacker can push out of the blockchain should be limited in some sense. Right, so the challenge in doing this, yeah, you want to ask a question? Right, so think of, okay, so let's imagine a scenario. I'm selling coffee every day. I know that I never sell more coffee than, $1,000 a day, right? That's what I do. So if you tell me the fraction of blocks that can get double spent is bounded, I can say my loss is bounded, right? Over a year, right? Of course, if there's a really large transaction, $1 million, this defeats the bound, right? But I'm not feeling very safe in that case, right? I might wait longer on the blockchain. But if somehow you give me a promise that the fraction is low, and I spread out payments over a long period of time, I won't get a lot of fraud. Right? You can think about it as credit cards. Credit cards, you often get paid as a merchant with a stolen credit card. But it doesn't happen very, very often, so you can live with it, right? So this is another notion of defense. It's basically we need to talk about costs and not about probabilities. Probabilities don't matter much, right? Also, if the probability of getting attacked is low, you need to think about the amount of money that you're going to pay, right? So again, we have to think about the fraction of blocks. Now, the problem with the classic analysis for Bitcoin security is that it consists of two phases, basically. One is where you think about the attacker building confirmations, and then there is a block race here that runs basically infinitely. The attacker tries forever to catch up with the network. He doesn't reset the attack and try again. So that's the classic analysis for double spending. But we need to account for these clever attack resets that I showed you, right? If I want to double spend a large fraction of the blocks, and I see I'm falling behind, maybe I want to restart my attack and so on, right? So I can do this as well, right? Maybe restart the attack, release transactions and so on, do these fancy things. So again, we can think of exactly the same technique using MDPs. We can combine this fraction approach with MDPs, we can get results, right? We just need to be careful to watch out that the fraction of double spent accepted blocks is not the same as the fraction of attacker blocks that were displaced. For example, if this block gets displaced and we were waiting for 2 confirmations, then this doesn't constitute a successful attack because you didn't buy coffee. I was waiting for 2 confirmations. You only got 1, so you didn't get the product. In this case, this block was double spent successfully because I was waiting for 2 confirmations. I got them, but then this block was thrown out. Right? So we need to kind of adjust the MDP, and here's the adjusted one. And we get a different level of security. Right? So this table basically includes our analysis of the protocol. If you have an attacker of size alpha, this is alpha, how much hash rate the attacker has, and this is how many blocks you wait basically before you give somebody a product, right? Before you assume money is yours. This is the fraction of blocks that you might get attacked on, the maximal fraction. And we've done this algorithmically rather than analytically. Right? We can fill up the table. And again, the policies are surprising. You sometimes wait and keep working on secret chains even though you're behind. And sometimes you give up. Right? So this is a policy for double spending 2 confirmations. You see that the only override here starts at 2 when the honest network has 2 blocks. Right? So you don't override when you are ahead by 1 because that doesn't help you. OK, so now I'll conclude. We're out of time. So what we basically showed is a technique to kind of find these optimal selfish mining deviations. It leads, I think, to a better understanding of the security of Bitcoin in general, right? And the ties between chain quality and security of the protocol. So some of the future work that you might be interested in or following up is think of the acceptance policy of a defender, right? Choosing this K, how many blocks to wait for, and the attacker policy basically as a game. There are 2 participants here, the attacker and the defender. The defender, if he chooses a large K, he pays by waiting very long for transactions to be accepted. The attacker has a monetary gain if he succeeds in an attack. And we haven't done the analysis as a game, basically only as a decision problem. You might model delay for, right, in this case for transaction confirmation as the cost for the defender. And finally, there's a way to do policies that are dependent on the transaction amounts if you want to bound your losses. So I think I'll stop here, and thank you all.